an interesting section. Kind of just throws in a bunch of extra stuff at the end just to make sure we're all on the same page. And I will say, if you look, we still have triangle angle sum theorem and side lengths versus opposite lengths to discuss. So that should come up in this lesson right now. So here we go. So Marcos decided to change his tiling pattern by drawing diagonals in each of the parallelograms. Find this pattern. And it sort of looks like, well, it sort of looks like this. Shoot. I thought I already opened it. Bummer. Sort of looks like this, right? So it says, from the resource page, copy one of Marcus's triangles on tracing paper. Use colored pen or pencil to shade one of the triangle's angles on the tracing paper. Then use the same color to shade every angle on the resource page that is congruent to the shaded angle. Repeat this process for the other two angles. So let's go ahead and see what that's going to look like. Again, I'll go with the orange. I've been having good luck with the orange. So I'm just going to go ahead and make all my orange. So what's going to happen here? It looks like this sort of flips up and this is also orange. I hope you guys are okay with that. So I will go ahead and fill in these ones as well. Now, if I had green, this would be green and this would be green. This is green, green, and green, and green. But also, I think if it flipped up, this would also be green. So hopefully we see, just depending on the orientation of the triangle, we get one color or the other. And then obviously all the rest will be this color. So this will be the last color that we'll sort of go with. And a couple of relationships that hopefully will jump out to you immediately would be the idea of vertical angles being congruent, right? You see that the greens are vertical and congruent, the blues are vertical and congruent, and the oranges are vertical and congruent. So I feel pretty good about what we did here. It seems like I did it okay. Maybe I made a mistake, but I think it's pretty okay. All right, so let's go back and keep going here. It says, now examine your colored tiling. What relationship can you find among the three different colored angles? What does this tell you about the angles in a triangle? Write a conjecture if in the form of a conditional statement. So obviously we've been talking about conditional statements, so like the if-then statement, right? So hopefully we're okay with that. But if we go back over here, I want you to look at something here. I'll go ahead and I'll circle it in black. Look, I have a straight line and I have each of the three colors. I have a straight line and I have each of the three colors. So anywhere I have the three colors, you'll notice I have a straight line. And what's interesting about that is, guess what these are? Each different angle of the triangle, which means triangles add up to how many degrees? It looks like a triangle adds up to 180 degrees. Again, because I have each there and it makes a straight line. So if you actually drew a triangle and cut the angles out of each and lined them up next to each other, you would get a straight line, and that would be 180 degrees. So that is one way you can get a straight line. All right, so it says, I'm sorry, it says if a polygon is a triangle, then the measures of its angles equal 180 degrees, I think, right? If you add them up, they add up to 180 degrees. It says, how can you convince yourself that your conjecture is true for all triangles? Well, they give us this handy dandy tool, this tool right here. You'll notice they have the angles, right? So 82 plus 45 plus 53 equals 180 degrees. This is the sum of A, B, and C. And you'll see, no matter what I do to these triangles, you'll notice, I pointed with my finger, you'll notice this never changes. So you can see angles A, B, and C change, but you will notice that the sum never changes. No matter what I do, I always get 180 degrees. So again, that is known as the triangle angle sum theorem, that all triangles add up to 180 degrees. So hopefully we will go ahead and fill that in. So moving along here. It says triangle inequality conjecture. Now that you have proven the triangle angle sum theorem, you can always determine the third angle measure of a triangle if you know the measure of the other two angles. This is kind of true. You can figure out a range for the third side. Oh, no, I'm sorry. I misread it. I was jumping down here already. So you can always figure out the third angle, right? If I told you one was 50 and one was 50, that's 100 degrees. You know the third angle has to be 80 degrees. So is there a similar relationship among the side lengths of a triangle? That is, if you know two side lengths of a triangle, can you determine the length of the third side? So first discuss with your team. Consider the specific case. Do we know what this side length is? And it turns out we don't know, but we can figure out a range. Jenny says that the third side could be any length. Mary says that's not true. For example, the third side cannot be 100. Who's correct? Well, it couldn't be 100. So let's go ahead and look here. Here's how we know this couldn't be 100. So let's say, what sides were they? I'm sorry. So they went 8 and 6. So if we go with 8 and 6, I'll make this one 6 and I'll make this one 8, right? Could this one be 25? Well, let's see. Are you ever going to close this triangle? You can't possibly close this triangle, right? If I laid it flat, you'll notice it doesn't close. If I went over here, this one won't reach it. So yeah, I would say this couldn't be 25. Here's what it could be. What if I made this 14? And if you're wondering where I got 14 from, what is 6 plus 8? 6 plus 8 is 14. Well, if I put this down at 14 and I lay this down with it, is that a triangle? It is not a triangle. But what if I made it a little bit less than 14? Now, all of a sudden, I can get it to close, right? So that's the trick, that you need to be able to get the thing to close. I'm having a lot of trouble getting it to close, but there we go, right? Now, what if I subtracted it and got 2, right? What if I put this thing down at 2? Can I get this thing to close? Well, if I lay this flat and I lay this flat, I'm sorry, I did that. I need to flip this thing over. You'll notice I get another straight line. So it's got to be more than 2, right? If it's more than 2, then I can get this thing to close. So kind of interestingly, that I have a range of triangles. Actually, I guess I don't even have a spot for it, which I should. That's kind of a bummer. But what we do here, maybe I need to change that. I don't know. We'll see. Probably I won't. But we can figure out a range from the other one by adding and subtracting the two sides. So if I add 6 plus 8 and get 14, and I subtract 8 minus 6 and get 2, my range is going to be between that. Let me set this up. And I'm sorry, what I'm saying is if I add 6 plus 8 and get 14, oh my goodness, why is life so hard? If I add 6 plus 8 and get 14, and I subtract 8 minus 6 and get 2, this becomes my range. My third side has to be more than 2, but less than 14. And again, I hope we saw that. I know I maybe didn't do the greatest job over here of proving that, but it's got to be between 2 and 8. Anything I pick between 2 and 14, anything I pick between 2 and 14 will indeed close this triangle. So anything between 2 and 14 will be okay. But if it's bigger than 14, that won't close. And if it's less than 2, that won't close, right? It's just not, it makes a little gator arm. It's not going to close that triangle. So I know between 2 and 14, and by the way, 2 and 14 are boundaries that are false because, again, 2 and 14 actually make it a straight line. There is no sort of like rise to that triangle. It would have to be more than 2 to give that triangle a little bit of rise. So hopefully we're okay with that. So what does that mean? Well, that means if I go over here, could these be a triangle? Well, I'll take two numbers. It doesn't matter which two I pick. Let's say I take 5 and 3. If I add 5 plus 3, I get 8. And if I subtract 5 minus 3, I get 2. That means the third side needs to be between 2 and 8. Is it? It is not. So this couldn't be a triangle. But what if you didn't pick 5 and 3? What if instead you chose 3 and 10? Well, 10 plus 3 is 13. And 10 minus 3 is 7. 5 would need to be between 7 and 13, and it's not. So I'm saying this won't be a triangle. 5, 3, and 10 will not be a triangle. So let's jump back over here. We'll go 5, 3, and 10, and I'm saying that you will not be able to get this thing to close. By the way, I think I should make this one the 10. It's so much easier to make that the middle. Okay, so look, these won't close. I drop that, I drop that. There's a gap there. It doesn't work. So that triangle can't possibly work. All right, what if I go here? 4 plus 12 is 16. And 12 minus 4 is 8. So is 9 between 8 and 16? Yeah. So I would say yes, this could be a triangle. So 4, 12, and 9. So let's go back over here. Again, we'll make that the middle one. We'll make this 4. And we'll make this one 9. And I'm saying this could work. And you can see right there, now look, right off the bat, it pretty much closes. So there you go. That triangle does make sense. The 4, 12, 9 does make sense. What about this one? 5 plus 2 is 7. 5 minus 2 is 3. 4 falls between this. So yeah, I'll say this would be a triangle. 4 falls between 3 and 7. So a 5, 2, 4 triangle should close no problem. So we'll make this one 5. We'll make this one 2. And we should be able to get this thing to close. And there you go. 5, 2, 4 triangle makes a lot of sense. It does close. And finally, a 3, 5, 8. Well, 3 plus 5 is 8. And a 5 minus 3 is 2. Does 8 fall between 2 and 8? No, it doesn't. 8 is not less than 8. Remember, it's got to be between these, not equal to. So I'm going to say no, this one won't close. A 3, 5, 8. So let's go prove that a 3, 5, 8 won't close. So there's my 3, there's my 8, and what I suspect is I should get a straight line because they actually perfectly equal each other. And there we go, it's got to be a straight line, so that is not a triangle. So hopefully we're okay with what's going on there. All right, to finish this up, the longest side, largest angle conjecture. When Marie was building triangles, she noticed another relationship. To make a triangle with one side length much longer than the other two, she had to make one of the angles much larger than the angle. She measured the angles of one of her triangles and drew the figure, right? So here's what we notice here, that the biggest angle is across from the biggest side, and that the smallest angle is across from the smallest side, and that the middle angle is across from the middle side. And is that always true? Well, they give us this pretty cool thing here to show that's the case. So what I want you to notice is the biggest angle is across from the biggest side, the smallest angle is across from the smallest side, the middle angle is across from the middle side. And if I change these things, there we go. Smallest angle, smallest side, biggest angle, biggest side, middle is the middle. What if I change it this way? Smallest, smallest, middle, middle, largest, largest. What if I have them be exactly the same? So let's wish me luck as I try to make them the same. There's some rounding going on there. That's a bit frustrating. Oh. Okay. So much of a pain for me to do this. Alright, let me pause this and see if I can get this right. That's why I hate these tools. The angles are the same. Hey, look, the sides across are the same. And this angle's smaller than these angles, so this side should be smaller. So there we go. We've kind of gone and proven a little bit the side's length versus opposite angles. So the longest side is across from the biggest angle, the middle side is across from the middle angle, the short side is across from the smallest angle. So that is something that we feel pretty comfortable with. So as we go here, let me go ahead and set up the end of this and then we'll call it a chapter. I did need this one. So anyway, we'll answer 107 here, then I'll jump to 108. It says determine EDF is a right angle. The measure of angle D is 90 degrees. Triangle EDF is a right angle. Measure of angle D equals 90 degrees. Julie thinks EF must be the longest side. In triangle EDF. Joey says, no way, we don't have enough information. So let's go ahead and see what we think here. So if D is 90 degrees, EF. Well, think about it. Could one of these angles be more than 90? It couldn't. There's only 180 degrees in a triangle. If this is 90 of it, the most this could be would be like 89.999, right? So I would say that, yeah, EF would have to be the longest side. So I would say that Joey's wrong and that Julie is right. Now let me go ahead and set up the last problem. We are going with our, oh yeah, that's right. It doesn't show up on the sheet. I keep forgetting it doesn't show up on the sheet, darn it. Okay, so we're going with the idea that we can figure out the range here. And again, my range of the side here would have to be between 32 and 6. So 6 is less than or equal to x is less than, oh wait, it's not equal to, god dang it. I think I put equal to earlier. It's not equal to. I'm going to have to go back and make a correction in this video, although I should make corrections in a lot of videos. But long story short, it can't be equal to, right? Because we proved that it's equal to. It makes a straight line. So it's not equal to. Here, 15 plus 14 is 29, and 15 minus 14 is 1. So again, this has to be between 1 and 29. It can't equal 1. It can't equal to 29. And then what about this one? Well, we would say this one is going to be between a plus b and a minus c, right? So we'll say a minus c is less than x, and that's less than a plus b. So there we go. That's our relationship for the third side. And again, I'm going to have to go back through and watch this video and point out that this should not have been equal to earlier in the video. So I apologize for that.